ever tap on your phone screen or, see a camera flash go off and just take it for granted.
It happens all the time.
Right. Well, these everyday things, they rely on something called a capacitor. It stores and releases energy incredibly fast. Today, we're doing a deep dive into these little powerhouses.
Yeah, and our guide for this is mainly the information laid out in capacitor.pdf. It gives us a really solid base.
What does it cover?
Pretty much the fundamentals, how capacitance is determined, how capacitors work together in series or parallel circuits,
Right.
how they store energy, and also the role of those insulating materials, the dielectrics.
Got it. So our plan, our mission is to kind of cut through the really dense technical stuff.
Right.
And pull out the really interesting bits about how these things actually work and why they matter so much in the tech we all use.
We want you to get a real feel for these unsung heroes of electronics.
Exactly. So let's start right at the beginning. What is a capacitor, fundamentally?
Okay, well, in its simplest form, think of it as two electrical conductors. They're positioned really close to each other, but they're not actually touching. That separation is key.
And that setup lets it do what?
It allows it to store electric charge. It's a bit like a tiny, very fast-acting battery in some ways, but it stores energy differently.
Okay, storing charge. So how do we measure that ability to store charge?
That's where capacitance comes in. There's a fundamental relationship, Q equals C times V.
QCV.
Yeah. Q is the charge stored, V is the voltage, like the electrical pressure, across the capacitor.
And C.
And C is the capacitance. It's the measure of how much charge Q the capacitor can hold for a specific voltage, V.
And the unit for that is?
It's the farad, symbolized with an F. So 1 farad means it can store 1 coulomb of charge if you apply 1 volt across it.
1 farad. That sounds
Right.
substantial. I hear it's actually a pretty big unit in practice.
Oh, it's huge, yeah. For most common electronic components, anyway.
So how is this capacitance determined? Our source material talks about parallel plate capacitors as a kind of basic example.
They're a great starting point, definitely. Just picture 2 flat conductive plates.
Okay.
Positioned parallel to each other face to face with a small gap in between, often just air in that gap.
Right.
Now, if you put a positive charge, say plus Q, on one plate and an equal negative charge, Q, on the other, you create an electric field, E, in the space between them.
Okay.
And the notes give us the strength of that field, E equals Q divided by AA.
Okay. Q is charge, A is the plate area. What's epsilon naught? AA.
That's the permittivity of free space. It's a fundamental constant that basically tells you how easily an electric field can set itself up in a vacuum, or air, pretty much.
Got it. So more charge, or smaller plates, means a stronger field. Makes intuitive sense. How does voltage fit in?
Well, the voltage, or the potential difference, VBA, between those plates is directly related to that field E and the distance D separating the plates.
Awesome.
The formula is VBA equals E times D. And since we know E equals Q or A, we can substitute that in.
So VBA equals Q day A.
Exactly. Now remember, our first equation, Q equals CV. We can rearrange that to C equals QV.
Right.
So if we plug in our expression for VC equals Q divided by Q day A, the Q's cancel out.
And you're left with C equals AA.
Precisely. That's the capacitance for a parallel plate capacitor in a vacuum or air.
Okay, so capacitance goes up if the plate area A is bigger.
Yep, more area to hold charge.
And it also goes up if the distance D between the plates is smaller.
Correct. Closer plates mean a stronger interaction, essentially.
Our notes have example 24:1 here. Let's try and make this a bit more concrete.
Okay.
Part A gives us a parallel plate capacitor. Plates are 20 centimeters by 3.0 centimeters, and the air gap is 1.0 millimeter. Calculate the capacitance.
Right. First things first. Units. Always watch the units. Area A is 20 centimeters times 3 centimeters, which is 60 square centimeter.
Which is 0.0006 square meters.
Perfect. And the distance D is 1.0 millimeters, or 0.00010 meters. Now we use C equals A arrow. Epsilon naught is about 8.85 times 10 to the minus 12 farads per meter.
Okay, plugging those in. C, 8.85 by 10 RFM or 1 FM, 0.000060 meters.
Crunching those numbers, you get about 53.1 times 10 to the minus 12 farads.
Which is 53.1 picofarads.
TF.
Yeah.
Exactly. Picofarads. See? Tiny.
Very tiny. Okay, part B then asks, what's the charge on each plate if you connect this capacitor to a 12-volt battery?
Now we go back to QCV.
Right.
So Curio 53.1 Areo F times 12V.
That gives about 6.37 times 10 to the minus 10 coulombs.
Yep. So one plate gets plus 6.37 by 10 ROC. The other gets negative 6.37 by 10 ROC.
And part C? the electric field between the plates?
For parallel plates, the field is pretty uniform. We can use the simpler E equals 0 VD relationship,
Ah, okay, so E equals 12 volts divided by 0.0000 meters.
which is 12,000 volts per meter.
Still seems like a strong field. Now, part D is where it gets kind of mind-bending. It asks for the plate area needed to get a capacitance of 1 whole farad with that same 1 millimeter error gap.
Yeah, this really shows you why the farad is such a massive unit for this kind of simple setup. We rearrange C, act as add, to solve for A.
So A equals C dash.
All right, plug in C, 1 farad, D equals 0.010 meters, and A equals 1F, 0.0010 meters, 8.85, 5, and 10 FMA.
And the result is?
It comes out to roughly 1.13 times 10 to the 8 square meters.
113 million square meters.
Yeah.
That's what, over 10 kilometers by 10 kilometers, like a huge chunk of a city.
Exactly. Utterly impractical to build a 1 farad capacitor that way.
Wow. It really drives home the point.
And this is a crucial but mentioned in the notes.
Yeah.
Today, we do have capacitors, even supercapacitors, with values of 1 farad or much, much more, and they are not 10 kilometers wide.
How?
Advanced materials and techniques. The notes mention activated carbon. It has an incredibly complex porous structure at the microscopic level.
So it creates a massive effective surface area.
Immense. The notes say just 0.1 grams of activated carbon can effectively act like a capacitor with about 1 farad of capacitance.
0.1 grams. Compared to 113 million square meters of flat plates.
It's a staggering difference. It's all about maximizing that surface area A and minimizing the effective separation D at the nanoscale. This is fundamental to how we miniaturize electronics.
That comparison is fantastic. Really shows the power of material science.
Okay, the notes also briefly mention cylindrical capacitors in example 24-2. What's the basic idea there? Not the whole derivation, just the concept.
Okay, imagine a central wire or a cylinder with radius RB, and around it, perfectly centered, is another conductive cylindrical shell with an inner radius ρ. The length L is much bigger than the gap between them, ρ RB.
Like a coaxial cable.
Exactly like a coax cable. That's a perfect example. Again, you charge one conductor with plus Q, the other with minus Q.
And the shape affects the capacitance.
It does. The electric field lines spread out radially, differently than between flat plates. The example in the notes would derive a specific formula for C based on ρ RB and the length L. The key point is just that geometry matters. Makes sense. Okay, so we know what they are, how capacitance is determined for some shapes. What happens when we put them together in circuits? Let's talk parallel first.
Right, capacitors in parallel. Imagine connecting them side by side across the same 2 points in a circuit.
So they all have the same connection points to the battery, for instance.
Precisely. That means the voltage V across each capacitor in parallel is exactly the same.
Okay, same voltage. What about the total capacitance?
It just adds up. The equivalent capacitance, SiC, is simply C plus C0 plus C and so on for however many you have in parallel.
Ah, simple addition. Why is that?
Because you're essentially increasing the total plate area available to store charge at that specific voltage. More area, more capacitance.
Like connecting water tanks side by side at the same level. The total storage volume increases. Okay, what about connecting them in series?
Series is end-to-end. The positive plate of one connects to the negative plate of the next, and so on, forming a chain.
Okay. And what's constant there?
In series, the charge Q on each capacitor is the same.
Why is that?
Because charge has to be conserved. Whatever charge flows onto the first plate must displace the same amount of charge through the chain.
Okay, same charge.
Yeah.
Different voltages across each one then.
Yes, the voltages add up. The total voltage across the series string is VIA plus VO plus VIA.
And the equivalent capacitance, is it just additive, like parallel?
So, no, it's a bit trickier. It's the reciprocals that add up. So 1 divided by SiC equals 1C arrow plus 1C arrow plus 1C.
It's 1 over C EQ. Okay, so you calculate that sum, and then you have to flip it, take the reciprocal again, to find SiC itself.
Exactly. And an important consequence is that the equivalent capacitance in series is always less than the smallest individual capacitance in the chain.
Less. Huh. So series connections reduce the overall capacitance.
For a given total voltage, yes. Think of it like the narrowest pipe limiting the flow. The smallest capacitor limits the overall charge storage capability for the series combination at a given voltage.
Interesting trade-off. Same charge, but lower total capacitance. Our notes mention a few examples, 24-5, 6, and 7, that use these rules. We don't have the diagrams, but they'd involve figuring out SiC for mixed circuits or finding the charge and voltage on each capacitor in a given network.
Right. You'd break the circuit down, identify series and parallel sections, calculate equivalent capacitances step by step, and then maybe work backwards to find individual charges and voltages using QCV and the series parallel rules.
Example 24/7 sounds particularly interesting. It describes charging two capacitors in parallel, disconnecting them, and then reconnecting them positive plate to negative plate.
Ah, yes. That's a classic charge redistribution problem.
How that happened?
Well, initially they're charged to the source voltage. Let's say CAUR and CO connected to V. They get charges QSU and QSUV.
Okay, then they're disconnected.
So they hold those charges. Then you connect C's positive plate to C's negative plate, and C's negative to C's positive. Exactly. Now charge can flow between them until they reach a new equilibrium, a new common voltage. The key is that the total charge is conserved, but since you connected them oppositely, the effective total charge available for the new combination is QQ.
Ah, the difference in the initial charges.
Right. And that total charge, QU euro, then redistributes across the total capacitance, which is C euro plus C euro, because they're now effectively in parallel again, until they reach a final voltage V final equals Q euro plus C.
And then you can find the final charge on each one. Fascinating. Shows how charge conservation is key.
Absolutely. These circuit analysis skills are fundamental.
Like storing charge logically leads to storing energy. How much energy is stored in a capacitor?
The energy stored, U, is equal to the work done to charge it up, to move that charge Q onto the plates against the electric field as the voltage builds up.
And the formula.
There are three equivalent ways to write it, which is handy. U 1/2 C times V squared.
U SEV euro. Okay.
You can also use QCV to substitute, so it's also U 1/2 Q squared divided by C. And finally, U 1/2 Q times V.
U half QV. Got it. Use whichever is most convenient.
Exactly. Depends on whether you know C and V or Q and C or Q and V.
Let's look at example 24/28, the camera flash. It says it uses a 150 microfarad capacitor charged to 200 volts. Part A, find the stored energy.
Okay, we know C 150 Mario F or 150 by 10 OF and V 200 V. So UXB half CB seems best.
U out 0.5, 150 to 1F, 200 V.
Let's see. 200 squared is 40,000. Half of 150 is 75. So 75 10 0, 40,000.
That comes out to 3.0 joules.
3 joules. Not a huge amount of energy in absolute terms. Maybe enough to lift an apple a few meters.
Right. But part B asks about the power if nearly all this energy is released in just 1.0 millisecond.
Now that's where the capacitor shines. Power is energy divided by time.
So power up to 3.0 joules with 0.001 in 0 seconds.
Which is 3,000 joules per second or 3,000 watts.
3 kilowatts. That's a lot of power, even for a tiny fraction of a second.
That's why the flash is so intense. It dumps that stored energy very, very quickly. High power output.
Explains the brightness. Okay, conceptual example 24/9 presents a different scenario. A charged parallel plate capacitor is disconnected from the battery. So Q is constant.
Right, charge is trapped on the plates.
Then, someone pulls the plates further apart, increasing the separation D. What happens to the stored energy?
Okay, Q is constant. We know capacitance C equals A area. If D increases, C decreases.
C gets smaller.
Now let's look at the energy formula. U equals half QRC.
If Q is constant and C in the denominator gets smaller,
then the stored energy U must increase.
The energy goes up. But where does it come from?
It comes from the work you do pulling the plates apart. The positive and negative plates attract each other. You have to exert a force and do work against that electrostatic attraction to increase the separation. That work gets stored as additional electrical potential energy in the capacitor.
Clever. So work done increases stored energy here. The notes also mention energy density. What's that about?
Energy density is just the stored energy per unit volume. For an electric field, it's given by U 1/2 arrows times E squared. U, all O's, A arrow A.
Energy per volume in the field itself.
Yeah. And the cool thing is, this formula holds true for any electric field, not just the one inside a capacitor. It tells you how much energy is stored in space wherever an electric field exists.
Interesting concept. And a very important safety note here too, right?
Crucial. Capacitors, especially large ones or those charged to high voltages like in power supplies or old TVs, can store a dangerous amount of charge long after the power is turned off.
So they can still shock you even if the device is unplugged.
Absolutely. Always assume a capacitor might be charged and know how to safely discharge it before working on related circuitry. It's a serious hazard if mishandled.
Good warning. Okay, final big topic, dielectrics. What are they, and what do they do?
A dielectric is basically an insulating material. Think plastic, rubber, ceramic, paper, even pure water. It doesn't conduct electricity easily.
Okay, an insulator.
And every dielectric material has a property called its dielectric constant, represented by K, kappa. K is always greater than or equal to 1. For a vacuum, K1. For air, it's very close to 1. For other materials, it's higher.
And what happens if you stick one of these materials between the plates of a capacitor?
It increases the capacitance.
Increases it. Yeah.
The formula for a parallel plate capacitor with a dielectric filling the gap becomes C cos K times A.
So it just multiplies the original capacitance by this factor K?
Pretty much. Sometimes people combine K and A into a single property called the permittivity of the material, epsilon, where 8. Then the formula is just C equals killed.
Why does putting an insulator in there help store more charge?
It's down to the molecular level. When you put a dielectric in the electric field between the plates, the molecules of the dielectric tend to polarize. Their own internal positive and negative charges shift slightly, aligning with the external field.
Okay, they stretch or rotate.
Right. And this alignment creates a small internal electric field within the dielectric that actually opposes the main field from the plates.
So the net electric field inside gets weaker.
Exactly. The overall electric field strength E between the plates is reduced for the same amount of charge Q in all the plates. Since voltage V equals Z, if E is reduced, then V is reduced for the same Q.
And since C equals QV, if V goes down for the same Q,
capacitance C goes up. You can store more charge Q for the same applied voltage V compared to having a vacuum there.
that makes sense. The dielectric kind of shields the plates from each other a bit, allowing more charge to pile up before the voltage limit is reached.
That's a good way to think about it. Example 2411 walks through a case like this.
Right. It gives a capacitor filled with a dielectric, K3.4, connected to a 100V battery. Plates are 4.0 meter area, 4.0 millimeter separation.
Okay, so initially connected to the battery, V100V, the capacitance C equals K. You can calculate that.
Comes out to about 3.01 by 10 OA, or 30.1 NF.
Then the charge Q with a CV equals 3.1 by 10 OF, 100V, 3.01 by 10 OC.
Or 3.01 NF.
And the field E equals 100V is 0.004 mejoule equals 25,000 diameter.
And energy U equals half CV, a 1.51 by 10 OA. Okay, that's part A. Now, part B says the battery is disconnected and then the dielectric is carefully pulled out without losing charge or changing D.
Okay, crucial step. Battery disconnected. What stays constant?
The charge, Q, it's stuck there. Q at 3.01 E.
Right. Now we remove the dielectric, so K goes from 3.4 back down to 1 for air. What happens to capacitance?
The new capacitance C will be CK, right? So 30.1 NF, 3.4 E out, it decreases significantly.
Capacitance drops. Now, what about the voltage V across the plates? We know Q and C, V, QC.
V 3.01 by 10 UAC, 8.85 by 10 UF at 340 volts.
The voltage shits up from 100V to 340V.
Wow. And electric field E, since VE is 340V, 0.004 meters, 85,000 VM.
Shield strength increases too. What about the stored energy? U? We can use U here, TC?
Since C is smaller than C and Q is the same, U must be larger than U.
Exactly. Calculating it gives you 5.4 by 10 UO, which is 3.4 times the original energy.
So just like pulling the plates apart, pulling the dielectric out of an isolated capacitor requires work, and that work increases the stored energy.
Precisely. You have to pull the dielectric against the electrostatic forces trying to keep it inside the field.
Fascinating stuff.
Okay.
Well, let's try to wrap this up. We've covered quite a bit.
We have.
Capacitors, basically two nearby conductors storing charge, governed by QCV.
Right, where capacitance C depends on geometry like add for parallel plates and the material between them.
We saw how they add up in parallel, SEC, CPC, and how the reciprocals add in series. 1 CA to 1 CR plus 1 CR.
Which is crucial for circuit analysis.
And they store energy, U a half CVR, which can be released very quickly, like in a camera flash.
And that energy actually resides in the electric field itself, with an energy density related to E squared.
And finally, putting a dielectric material, an insulator with K1, between the plates increases capacitance by reducing the internal electric field,
allowing more charge storage for a given voltage.
It really ties back to those everyday things. Keyboards often use capacitance changes to detect key presses. Flashes use rapid energy discharge.
Absolutely. And some of those details were quite striking, weren't they?
Definitely. That calculation for the 1 farad parallel plate capacitor needing an area 10 kilometers by 10 kilometers.
Yeah, compared to 0.1 grams of activated carbon achieving the same thing. Shows the power of nanoengineering.
And also, that counterintuitive result of removing a dielectric from an isolated capacitor charge stays constant, but voltage and energy increase.
Because you have to do work to remove it.
It really does make you think differently about the electronics all around us. So maybe something for you, the listener, to ponder.
Yeah.
Given this constant push for better energy storage for phones, laptops, electric cars, grid storage, what do you think the next big leaps in capacitor technology might look like? Better materials, new designs?
Or maybe even thinking broader. Could these core principles of storing and rapidly releasing electrical energy find applications in fields we haven't even thought of yet?
That's definitely food for thought. Something to mull over. Join us next time for another deep dive.